In section 5.4, we look at the irrational numbers. The number under the radical is called the radicand. The entire symbol is called a radical. The set of irrational numbers is the set of numbers whose decimal representations are neither terminating nor repeating. For example, a well-known irrational number is pi because there is no last digit in its decimal representation and it is not a repeating decimal. The United Nations building in New York was designed to represent its mission of promoting world harmony. Viewed from the front, the building looks like 3 rectangles stacked upon each other. In each rectangle, the width divided by the height is the square root of 5 plus 1 to 2, which is approximately 1.61821. The ancient Greeks believed that such a rectangle, called the golden rectangle, was the most pleasing of all rectangles. The principal square root of a non-negative number n, written the square root of n, is the non-negative number that when multiplied by itself gives n. So for example, the square root of 36 is equal to 6 because 6 times 6 equals 36. Notice that the square root of 36 is a rational number because 6 is a terminating decimal. However, not all square roots are irrational. A perfect square is a number that is the square of a whole number. For example, here are a few perfect squares. 0 squared is 0, 1, which is 1 squared, 4, which is 2 squared, and 9, which is 3 squared. The square root of a perfect square is a whole number. So the square root of 0 is 0, the square root of 1 is 1, square root of 4 is 2, and the square root of 9 is 3. So the product rule for square roots allows us to simplify square roots. So if a and b represent non-negative numbers, then the square root of a is equal to the square root of a times the square root of b. The square root of a product is the product of the square root. So all this is saying is I can split this apart into multiple square roots to simplify. However, the way that I like to teach it is not with this method because you have to really know your perfect squares or your perfect cubes, so on and so forth. So we're going to visit that factor tree again. So let's look at 75. We can break this down into 3 and 25. And 25 can be broken down into 5 and 5. So because this is a square root, we are looking for pairs of the same number. So because I have a pair of 5s, I can pull the 5 out front. We only need one of them. And anything that's left over is what will stay on the inside of our square root. So we end up with 5 square root of 3. Let's try 500. Well, we can break that down into 5 and 100. 100 is just 10 and 10. And we can break down both of our 10s into 2 and 5 and 2 and 5. So we have a pair of 2s and we have a pair of 5s. So we'll have 1 2 come out and we have 1 5 come out, and the only thing left over is the 5, and we end up with 10 square root of 5. Now for 17, the only two things I can break it apart as is 1 and 17. So because I don't have a pair of the same numbers, this entire thing is just going to stay underneath the square root. Now when we multiply square roots, we're going to use the other part of the product rule, which says that we can smush the two square roots together and then simplify. So the square root of 2 times the square root of 5, we can smush this underneath one radical, and we get the square root of 2 times 5. which is the square root of 10. And that can't be simplified. For the square root of 7 times the square root of 7, we smush it together, we get the square root of 7 times 7, which is the square root of 49. But the square root of 49 is going to give me my perfect square, and we've got 7. For the square root of 6 times the square root of 12, again we're going to simplify by pushing it together, which we get 6 times 12, which gives me the square root of 72. And we want to be able to break down 72. Well, that's 2 and 36, and 36 is 6 and 6, which both of those are going to give me 2 and 3. So we have a pair of 2's and a pair of 3's with a 2 left over. So we have 2 times 3 with the square root of 2, which gives me 6 times the square root of 2. Dividing square roots is like the product rule, except we're not breaking it apart horizontally, we're breaking it apart vertically. So I can have the square root of a over the square root of b, and that just becomes the square root of a over b, or vice versa. I can have the square root of a over b, and that's equal to the square root of a over the square root of b. So let's look at the square root of 75 over the square root of 3. I am going to put this all underneath one square root, and we get the square root of 75 over 3. But 75 over 3 is 25, and 25 is a perfect square, so we end up with just 5. Let's look at the square root of 90 over the square root of 2. So I'm going to split. We've got the square root of 90 over 2, which is the square root of 45. And we want to break that apart. Well, 45 is 5 and 9, and 9 is 3 and 3. So we have a pair of 3's that we can pull out with a 5 underneath. Now to add and subtract square roots, the number that multiplies a square root is called the square root's coefficient. Square roots with the same radicand can be added or subtracted by adding or subtracting their coefficients. So that radical needs to have the exact same thing underneath it to be able to add or subtract the coefficients together. So looking at the 7 times the square root of 2 plus 5 times the square root of 2, since we have the same radical, we just add the coefficients, 7 plus 5, and that's going to give me 12 square root of 2. Same idea goes for the second one. We have 2 root 5 minus 6 root 5, and 2 minus 6 is going to give me negative 4 times the square root of 5. Three root 7 plus 9 root 7 minus root 7. So same radicals. 3 plus 9 is going to give me 12, and 12 minus 1 is going to give me 11 square root of 7. Now what if the radicals don't look the same? Well, we want to see if we can simplify them so that we can add or subtract them together. So the square root of 2 is already simplified, but we can simplify 8. Eight is 2 and 4, and 4 is 2 and 2. So we can pull out a 2, and we have a 2 left over. So rewriting, we have the square root of 2 plus 2 root 2. And so when I add 1 plus 2 together, I end up with 3 square root of 2. Let's try something a little bit more complicated. I've got 4 square root of 50 minus 6 square root of 32. So let's look at the 50 first and simplify. That's 5 and 10, and this is 2 and 5. Well, we have a pair of 5s that we can pull out with a 2 left over, and let's do 32. That's 2 and 16. 16 is 4 and 4. And both of those are going to give me a 2 and 2. So I have a pair of 2s and another pair of 2s that I can pull out with 1 2 left over. So we have 4 times the square root of 50 is going to simplify as 5 square root of 2 minus 6 times the square root of 32 is going to simplify as 2 times 2 times the square root of 2. Well, 4 times 5 gives me 20 square root of 2. And we've got 6 times 2, which is 12, times 2 is 24. And 20 minus 24 is going to give me negative 4 square root of 2. And the last thing we're going to talk about is rationalizing denominators. We rationalize the denominator to rewrite the expression so that the denominator no longer contains any radicals. We want to multiply the numerator and the denominator by the smallest number that produces the square roots of a perfect square in the denominator. So we want to multiply the top and bottom by the denominator. So I have 15 over the square root of 6, and we're going to multiply the top and bottom by what the issue is, which is the square root of 6 in the denominator. And so when we multiply fractions, we multiply across the top, we get 15 square root of 6. And remember, we can multiply our radicals by multiplying the inside, which gives me 36. And the square root of 36 is 6. So you end up with 15 root 6 over 6. Let's look at the second one. The square root of 3 over 5. Well, the first thing that we can do is we can split it into 2 separate radicals. The square root of 3 over the square root of 5. And we need to get rid of that denominator. So we're going to multiply by the square root of 5 in the top and bottom. So we multiply across the top. That gives me the square root of 15. And we multiply across the bottom, which gives me the square root of 25. We can't simplify the square root of 15 at all, but the square root of 25 is 5. Having radicals in the numerator is 100% fine. It's just the denominator that causes issues. And the last one, we have 12 divided by the square root of 8. You could first try to simplify the radical a little further, or you could just multiply by the square root of 8 and simplify afterwards. So I am going to simplify the denominator a little bit. And so this is going to become 2 square root of 2. And you can use the factor tree to check. Now, What's causing the issue is just the square root of 2, not the 2 root 2. So we need to multiply the top and bottom by the square root of 2. So we end up with 12 square root of 2 over 2 times the square root of 4. Well, on the bottom, the square root of 4 is just 2. And so we have 12 root 2 all over 4. And we can simplify the 12 and the 4. 12 over 4 is just 3. And so we end up with 3 square root of 2 as our final answer.